At the outset, I would like to thank the Academy for the kind invitation, which I was glad to accept because this is a forum. I consider it as a privilege and honor to talk here and present some of the recent developments in the understanding of what is called the space weather. And we use the airglow and aurora as a means to understand what's happening up above in the sky. This is all we have seen. When you look at the night sky, we can see the stars, and we can see the stars because the Earth's upper atmosphere, or the whole regions of atmosphere, are transparent to the visible light. And we know that all stars emit in the whole electromagnetic spectrum. The same is true for our sun also. And then, but the other regions, other spectral regions that their emission is in X-rays, ultraviolet, UV, etc. They all show 11-year solar cycle. That's what is called solar cycle. This is every year picture taken by in the soft X-ray region, and you can see high solar activity here and low solar activity there. And but there's not much of variation in the visible. That's why on the ground we don't see the solar activity. So when this light comes onto the ground, Earth's upper atmosphere absorbs all these X-rays, UVs, and to some extent ultraviolet, and that's where there's exothermic reactions. That's why the temperature, if you see, it increases to 1500 or 2000 Kelvin in the high solar activity period, and in the solar minimum time, it will be under 1000 Kelvin. And this X-ray radiation ionizes the atmospheric constituents and atoms and molecules, and that's this red line that you see is the ionosphere that's formed. So the ionosphere allows has enough ionization to enough plasma to allow the radio propagation. And this combined ionosphere and thermosphere, they occupy the same real estate. So there's a lot of coupling between ionosphere and thermosphere, and this is the region where we see the brunt of the solar activity, CMEs and coronal mass ejections, and then the geomagnetic storms that happen, that originate from the sun, and they have interactions in the magnetosphere and come down. And this is the region wherein all the orbiting satellites of the Earth, they are in this region, and the plasma irregularities, because ionosphere thermospheric interactions that take place. So any plasma irregularities disturbs the communications, and this enhancement of temperature and that affects the satellite drag, and also with the human space activity being planned not just by even India now, it's all the more important that the radiation dosages need to be understood. So it's the space weather, this is the whole region is what is of concern here. The whole space weather is a highly interdisciplinary region of interest and research. And over on top of that, because Earth is a magnetized body, the ionosphere is a kind of birefringent medium, wherein the properties of light across the magnetic field lines and along magnetic field lines are different. So there are, purely from the fundamental science point of view also, the various phenomena that are happening from low to high latitudes, and which all now have become more and more important to understand for even the societal applications on the ground. So we studied through what is called the airglow and aurora. This airglow is a faint light that we can't see. That's why we can see the stars but not the airglow. But we know that it exists that because of its counterpart, the aurora, which is very bright and it's in high latitudes to mid latitudes, and it is formed by the interaction of solar wind origin magnetic particles with the ionospheric or upper atmospheric atoms and molecules. And these are some of the pictures that you see here. Is a very beautiful red color on the top, green on the bottom, and some whitish here, and that whitish comes because of purely combination of primary colors, RGB. So there is a blue there also, so that makes it white. And there are different shapes, and I'll not talk too much about aurora, but there's one more slide here. Sometimes it's all red. The Romans thought it was a blood in the sky because there used to be a lot of wars in the Europe, and and because this recorded history of aurora is there in the European in the catalogs. So, so aurora is basically really a cosmic TV picture tube. So we have all seen, we are aware of this CRTs, wherein there's a power source, electrons are produced here, and that is modulated by the electric fields, and then that that electron goes on to hits the phosphor screen on the tube, which gives us the image. So the same thing is happening here, in the sense that there is solar wind, magnetosphere is a generator, and these electrons get accelerated as they come through, and they're modulated by the magnetic field variations, and they hit in the upper atmosphere and the atoms and molecules, which get excited to their higher state, and when they come down to the lower state, they give out energy in the ultraviolet, visible and infrared region, forming a light. So that is the so-called phosphor screen in the Earth's case. So this is a loci of all the points where the magnetic field lines cave in into the Earth's upper atmosphere. It's a kind of oval in shape because of in the day side the solar wind pushes it, and it pushes the magnetic field lines, and that's why it's oval in shape. So this is a picture of Earth itself on a polar satellite. While these are the two pictures from Jupiter and Saturn. All magnetized planets will have aurora. So that's this example to give just to show that that this is what is happening. So just looking at these lights, we can study various things. So what can these lights tell us? If you are in high latitude, looking, the compass needle on the ground gets deflected when this aurora is happening. So that's how we discovered that these not just lights, but there are currents associated with that. Because of that, there is an induced magnetic field on the ground. These rays are actually, we can see the magnetic field lines become visible because of the particles coming in. The analysis of colors reveals different energies, because different energetic particles have different transitions that they enable, and therefore look at the ratios of the colors, you can talk about what is happening. Also, when you look at the constituent variations in constituents, that contribute to the airglow modulations, intensity modulation. So you can get neutral density variations, temperatures, you can derive gravity waves, tidal behavior, plasma neutral coupling between large and small fields of view. Several things that we can study just by looking at these airglow emissions from far away. So it's called passive remote sensing because we are not disturbing the medium. It's naturally there is some glow that's happening. We are studying from far away. So this is the thing that I wanted to say. Aurora and Airglow, which are the tracers of the weather in that in the ionosphere thermosphere region, and that's what it summarizes what I wanted to talk about in the broad introduction point of view. There are various wavelengths. I'll not go into them, but these are natural phenomena, so they occur all the time: nighttime, twilight time, daytime, and that's nomenclature is pretty standard. It's called night glow, twilight glow, and day glow. While there have been all measurement made from satellites, rockets, and ground based, and it should be appreciated that different emissions occur at different heights, and the altitude of an emission depends on the concentration of the reactants, rate, coefficients, and lifetime of the species. And but so how do we measure these emissions? For nighttime, it's not too difficult. More than 100 plus years of recorded history is there. You can have spectrums, images, photons collected on the ground, looking at devising simple experiments. But daytime, it's challenging, as solar scattered background is orders of magnitude larger than the day glow, and therefore it is required that we carry out high spectral resolution measurements to cut out the background. And it's also more because we are looking at multiple wavelengths, they emanate at different altitudes, so we would like to study multiple wavelengths at the same time. And also we want more and more studies. We want it to be capable to have large field of view, because so that we can study spatial variations of what are happening. So in that regard, we have come up with an innovative method in which we call this MISE, multi-wavelength imaging spectrograph, using a shell grating. So we use a shell grating to it works in high orders, and that the problem is of the order overlap. So not many people were using traditionally, but at the advent of the interference filters, we devised a method by which we can get multiple wavelengths at the same time in the same diffraction angle region. So there's no moving parts, no grating angle change is required. So what you see here is a front end optics, there's folding optics here, a collimator, grating, and then the imaging section. So the broad concept wise, it's pretty straightforward. So what you see here is the red line 7774 and 5577. These are the dotted lines, are the lines where the emissions occur. Emission region is there, and then this is a large spatial region, 140-degree field of view. As I said, different emissions come from different altitudes. So just looking at one particular location, you can scan what you can understand or study what is happening at multiple altitudes, 100, 300, 250 kilometers. These are the altitude regions. So that's the beauty of this method. So just to know how do we extract the day glow from the sky spectrum. So these are the two spectra I am showing here. It's at morning 5:45 local time. You can see this is the image. You see the Fraunhofer absorption lines are seen here in dark. You may be able to see there, the bright line there. That's where the twilight glow is. That's emission is. But as soon as the sun comes up above the horizon, you can see that white is not seen here. That doesn't mean that the glow is not there, but what it means is the background has increased. So the method we have come up is to really look at high resolutions. As I said, you compare the solar spectra in the blue here and the sky spectrum in the red here, and then these two, when you compare at a high resolution, you see that these can be different in terms of absorptions, emissions, and scattering. We know that there are no absorptions in this region, so there's only scattering and emission. You take the difference of them, and this is where the daytime air glow is, and we can take care of the scattering by a neighboring region, neighboring Fraunhofer line, which is almost the same depth. So there is a method, and then we have been successful in deriving this, in detecting this day glow from the ground and over a large field of view over multiple wavelengths. So again, the building new techniques is not the end of it. That's the beginning of the next work, and this has actually opened up new vistas, and several insightful and new results and discoveries have been made. And I here my attempt will be just to give a broad flavor of some of them. There is in any of the lower atmosphere, there are a lot of waves that are there, but as the atmospheric densities decrease, these waves grow in amplitude because of conservation of energy, but they can't go on infinitely because they break at some altitude, and then they generate secondary and tertiary waves which go up. So conventionally, this is the ionosphere thermosphere region. People were considered that it's purely affected by the solar effects, but what we have done here, all these first authors here are all my students. So this work in his PhD work, what was done is that we quantified it. We said that solar forcing when sunspot number is greater than 110, the ionosphere thermosphere is purely affected by the solar effect. If the sunspot number is below 35, it's purely from the lower atmosphere, and the transition region is this. It's very broad, but there are many other works that have come in, and this is one of the initial works that we had shown. Another result is in terms of longitudinal variability, because Earth's magnetic field anomalies are there at different locations, so that can cause the variations in the electrodynamics in the ionosphere. There are other things in terms of magnetic angle, declination angle, longitudinal strengths, and convective processes. They are present. So until our study by Deepak Karan here, the result was that the longitudinal differences exist in the electrodynamics for 10 degrees and beyond. But what we have shown here, now that we have a large field of view instrument, we looked at in the east and west directions. If these two, the green line is 100 kilometer emission, is the altitude of emission. So the difference between these two east and west arms is around 350 kilometers. If these two behave in the same fashion, there are longitudinal variabilities. If they behave differently, then there is a variability. So we have shown again for the first time that longitudinal variability can exist in as small as 3 degree separation, that is 350 kilometers or so. Another result is in terms of looking at these emissions from the ground. I was operating this experiment from Hyderabad, and we are looking at 3 wavelengths. These all 3 are oxygen emission lines, And we saw consistently that suddenly, for some duration, these emissions were enhancing. We ruled out all other possibilities. I'm not going to details. But then we said that only the thing that came out to was what is called the stratospheric sudden warming. That is a phenomena that occurs in the stratosphere of high latitudes in northern polar regions. When this warming happens, there is a cooling, mesospheric cooling associated with it, and then the low thermospheric warming. So you are seeing here, represented. This is a schematic we came out in that paper. We said that because of the stratospheric, this lower thermospheric warming, there is a physical transport of atoms from the high latitudes to low latitudes, which cause this emission enhancement, and this circulation is completed by the thermospheric interhemispheric winds that is going on from the summer to winter hemisphere. So we drew this picture saying that based on 4 years of consistent data, every stratospheric warming time we saw an enhancement here. So this tells about the latitudinal coupling that is happening, and we discovered a new circulation cell in the atmosphere based on the measurements here. There's another result in terms of, because all the waves and winds, they are related. This is a gravity wave dispersion relation given by Colin Hines, wherein there are horizontal wave vectors and then vertical wave vectors are related with the winds. Now we have a method wherein we have large field of view. So simultaneously measuring at large regions, we can get what is happening we can do wave number analysis and get the scale sizes. So this is a slit spectrograph. So we make the measurements in horizontal and meridional and zonal alternatingly, and then we have another method by come up with this Subir Mandal's thesis, wherein we can get the radio measurements to get the vertical wavelengths. So we are measuring kx, ky, kz. Now we plug in this equation and we get the neutral winds, which is again a very difficult, very tough parameter to get from the ground in the daytime. So this is a 3D characterization, and these are just a flavor of some of the experiments that we have been doing, and there are many more, but I have just wanted to give you a flavor based on this experiments, and we, because the importance of the space weather studies, we had proposed a mission called the Disha mission, and I named it Disha based on disturbed and quiet time ionosphere thermosystem at high altitudes. This Disha will be a dual aeronomy satellite mission. We will have 2 satellites, one going in the high inclination, one going in the low inclination, with optical photometers that I had just talked about, similar to that but in a different, adapted for space. That will say again, whole Indian missions, so the other institutions are also involved. This is auroral X-ray imager, visible airglow spectral imagers, Langmuir probes, drift meters, neutral mass spectrometer, electron temperature analyzer, and this is will be able to address some of the fundamental science questions, as well as the space weather applications are getting more and more important. Recently, some of the satellite laws that we have seen from some recent experiments from other countries, they're all result of the space weather effects or disturbances. So just to summarize, a new field of daytime optical aeronomy has been initiated at PRL, wherein I have just touched upon only one technique, but we have developed techniques for daytime and nighttime auroral measurements, which range from ultraviolet to infrared. We have flown these experiments from balloon from the high altitude balloon facility from Hyderabad, and there are fields of view are 140 degrees and 3 degrees, small and large, and low and high resolution, and several new results have come up, and several thesis PhDs have come up, and the students are very well placed and doing great work in other countries, and the use of such optical techniques and expertise is being extended to building optical instruments on board ISRO's science mission Disha. I just didn't talk about Venus. There is also we proposed a payload for Venus atmospheric studies also. So I'll acknowledge several of my collaborators, my Disha and Nava team members, and present former students, and my Department of Space. So these are all my students and former students and present students and my team, to whom I would like to say that they have all been part of this journey. And thank you very much for your attention.
I would like to hear from you. your comments on Arnav Rai Chaudhary's book, popular book, Nature's Third Cycle.
I I would not I have not gone through completely to comment on that. So maybe I'll reserve my comments. Okay, sorry.
Nice talk, Pallamraju.
Thank you.
I just wanted to know how well we predict these things, whether we are just looking at the effects of solar activity on the ionosphere, how in advance we can predict these things so that the commercial activity is so much increased.
Yes.
People really wanted to know that.
Yes. Okay. Thank you. That's a really speaking. That's the reason. That's the research that we are working on, and along with several of the colleagues. But to tell you here, as soon as there is a flare, and we know that associated CMEs would occur. So at least that is flares come in 8-minute time. And if there are CMEs, we can say fairly well that if there are CMEs there, depending on the solar wind speed, they'll come in 2-3 days time. So that is one of the warning. But that is nowadays, several papers also they are just giving up this, that there is going to be a solar storm. But then, as you would know, appreciate it, that is interplanetary magnetic field has to be southward in direction, orientation, to have the reconnection, magnetic reconnection has to happen. So the most critical question is in terms of how can we predict IMF BZ south. If that is the kind of, the reconnection happens, there's a gateway opens up. All the particles of solar wind origin can come in. If there is IMF BZ is northward, then there's a compression of Earth's magnetic field lines. As much, the gates are not yet open, so not many particles can come in. There are other studies that are going on in the solar studies in terms of chirality. At the time of the sunspot, at that origin, can you see the chirality? Okay, that is one. And also there are other statistical studies based on the sunspot should be facing earthward facing should be the one of the condition. If there is more other directions and the azimuthally farther away, then you can't then this likelihood of its affecting the earth is reduced. So these are the broad parameters. But then the most important critical thing is in terms of BZ south prediction. And in between there is interplanetary accelerations and decelerations are also happening. So that is the critical. So once that is done, then our present study talks about few days is the thing that we can say that is likelihood of coming. But exactly if it is going to hit or not, BZ, it depends. But we have satellites in L1 Lagrangian point, and the Aditya mission that's going to go up in a couple of months. The whole idea is to have these measurements done at the Lagrange point, so at least we'll get a very clear prediction of a year or 1 hour or 2, because from L1 point, Lagrange point to the geomagnetic conducting geomagnetic storms, that is the time. So 1.5 hour to 2 hours is what we will be possible.
Hello, sir. What
Yes.
are the experimental techniques you have followed to know about Aurora? What are the experimental techniques?
What are the
experimental techniques you are following to
Huh.
know about Aurora?
Okay, the Aurora has been we are carrying out experimental techniques. When I was there in the US, I had put instruments in sounders from Greenland and all. So all these optical techniques are I'm working on. But there are various radio techniques. There are various other radar measurements are going on, and there is Aurora is just a beautiful visible light to delight to see. But there are many other things that are happening. Plasma irregularities are getting formed, ionospheric currents are getting formed. So there are many other measurements that are going on, and traditionally Aurora there is a lot of information, because even from Greenlandic nomadic people also used to mark, from 500 years of record is there from Greenland. Whenever they saw Aurora, they had put some marks. So that is there. So scientific study past 100 years, a lot of study has happened.
Okay. Well, I'm sure there will be